Professor Pankaj S. Joshi is an eminent Indian physicist and cosmologist and a leading authority in general relativity, gravitation, and cosmology. He is currently Distinguished Professor of Physics and founding director of the International Centre for Space and Cosmology at Ahmedabad University in Gujarat, where he leads research, training, and public engagement in fundamental questions about the universe. Before joining Ahmedabad University, Professor Joshi was a senior professor in the Department of Astronomy and Astrophysics at the Tata Institute of Fundamental Research TIFR, Mumbai, where he carved an international reputation for his work on the gravitational collapse of massive stars and the nature of space-time singularities, including insights into black holes and the possibility of naked singularities. His research has been published in more than 200 peer-reviewed papers and major monographs from Oxford and Cambridge University Press. Invited by Stephen Hawking to work at Cambridge University under a Nuffield Foundation Fellowship early in his career, Professor Joshi has also held visiting positions at top institutions across the UK, USA, Japan, Spain, South Africa, and Italy. He is a fellow of leading scientific academics and a recipient of prestigious awards, including the INSA Vainabappu Memorial Award. Professor Joshi's contributions span deep theoretical advances and wider science outreach, making him one of the India's most respected figures in theoretical physics and cosmology. Without any further delay, it's my pleasure to invite Professor Joshi to deliver this talk.
Thank you. Okay, I would like to warmly thank the Bhaktivedanta Institution and all of you for this wonderful opportunity to be able to talk to you. So we will talk about the stars and the universe. There is a curiosity, as we know, right from the beginning on the stars, what they are. In the earlier days, we had the celestial sphere, and looking beyond the celestial sphere was kind of forbidden. Unknown forces might be there. But then it's in the nature of men to ask questions, to find out the laws of universe, and the quest continues. As of today, we have wonderful missions on the earth as well as out there in the cosmos, where we probe the universe to very depth, millions of kilometers away. We try and see. This is, of course, the Hubble Space Telescope, and this is the Chandra telescope, which observes the skies in X-rays. But apart from these classic instruments, many new projects are coming up, and some of them are already operational. They are square kilometer array, TMT 30-meter telescope, LIGO. LISA is in the workings. Even more importantly, the Event Horizon Telescope to observe the centers of the galaxies. I will talk about that. And also such others. The most important difference that has taken place because of all these missions is that we have started now on the on the deepest places in the universe, but at the same time very strong gravity, ultra strong gravity regions of the cosmos also we are really looking at. When we look deep into the skies, beyond what you see actually with naked eye, you see the dots in the sky, the telescopes show not only the stars but also what are called nebulae. And many of these objects that you see in this picture are actually big, massive galaxies. This is a close up of the previous picture, and each one of these galaxies, in fact, are 400 to 500 billions of stars. This is one of such galaxies. This is another galaxy. Galaxies come in various shapes and sizes. Uh, it's a huge issue today. So much data is actually coming in, but AI might help us to, you see, process this data much more effectively. There is a competition between the technology and the data coming in, so to say. But today I will focus mainly on stars rather than galaxies. And why stars? We will talk in a moment. The stars really and the black holes we will be talking about, which are at the centers, which could be at the centers of the galaxies. These are the objects which are of greatest interest today. The point that I wanted to make was that stars are sun-like, but then much bigger star than the sun, like the, you see, Sirius, Pollux, Arcturus, and so on. They all exist in the universe. Now, the life of sun is about 5 billion years today, and it is still going to live another 5 billion years. However, if the star is much more massive, say 10, 20, 30 times the mass of the sun, then its life is much shorter. In fact, it will live only, say, 10, 20, 30 crores of years, depending on its mass. The more the mass of the star, the faster, quicker are the internal burning processes within the star. And then what happens is that when the, you see, nuclear fuel within the star exists, then the star starts contracting under its own gravity. This is just another picture showing the size of Earth in comparison to Sun. So, how small the Earth is, and still so many things happening today on the Earth. As we all know, you see, today, the point is if we realize how tiny we are on the scale of cosmos, probably, you see, our egos can become smaller. You have just heard, probably, you see, the Big Bang theory and the origin of the universe. The universe is supposed to have originated from a Big Bang. Eventually, galaxies formed. And of course, we have Large Hadron Collider like experiments which also probe the very highest collisions of elementary or basic particles, so to say, in the universe. The key question, which has been one of the most prominent issues in cosmology as well as astrophysics, is what happens when a massive star dies. As I told you before a moment, very massive stars, like 20 or 30 times the mass of the sun, their lives are pretty short. It's like a balloon. You see, when you release the mouth of the balloon, the air goes away and the rubber contracts the size of the balloon. Similarly, a star that was existing for, you see, millions of years, within seconds or minutes, it contracts or collapses catastrophically under the force of its own gravity when its internal nuclear fuel is gone. Uh, what happens when such a star dies? In fact, Subramaniam Chandrasekhar's work, early work in the 1930s, was related to, you see, the final fate of sun-like stars. He pointed out that such stars collapse into a stable configuration. Uh, the stars which are about 1.4 solar masses, they result into white dwarf size, which is about 1,000 kilometers. Our sun also will one day become a white dwarf. Its outer layers will be thrown away, engulfing the planets around. In fact, Chandrasekhar pointed out, you see, that it must be taken as well established that the life history of a star of small mass must be essentially different from the life history of a star of large mass. So this was pointed out way back in 1935 that large stars, their life histories, you see, remains a big question. As he says at the end of this para, a star of large mass cannot pass into the white dwarf stage, and one is left speculating on other possibilities. So this has remained one of the most important questions in astrophysics and cosmology, also related to you see the high energy astrophysics. This is where what you have to do is to study the gravitational collapse of a massive star. And what is the final fate of such a star? This question was studied using general theory of relativity, because the gravitational fields are so strong that you need Einstein's theory of relativity. And in fact, this entire question is absolutely fundamental to the modern theory and the astrophysical questions related with black holes. Einstein theory has to be used. The key point is it is dealing with the curvatures of space and time. Uh, I cannot go into the details of the same, except I'll show you a few equations of the theory. But we are familiar with positive, negative, as well as you see flat surfaces. This is a kind of generalization, Riemannian geometry, dealing with the space-time continuum, the four-dimensional space-time manifold. Uh, and of course, Einstein gravity has important manifestations such as black holes, Big Bang, gravitational waves, and the shadows at the center of the galaxy. In 1939, Oppenheimer and Schneider wrote a paper uh, showing that there is a continual collapse happening. Then in that case, you see the entire spherical mass, the star, if you call it that way, will collapse to what is called a space-time singularity. When this singularity forms, before the singularity has developed, what will happen is an event horizon will happen. An event horizon will form, so singularity will be necessarily covered. What is singularity? It's a event, it's a place, it's a happening where all the mass of the star, according to the general theory of relativity, will be concentrated, you see, collapsed. Uh, it was the so-called cosmic censorship uh, due to Roger Penrose and also Stephen Hawking, at least partly, that they conjectured that when you consider more realistic collapse, I say more realistic collapse because the Oppenheimer and Schneider's work was based on very many special assumptions. That is, the star is completely spherical, the star is completely homogeneous, it is made of matter which is only dust, that is, it has no pressure, so on and so forth. And then what happened was the star collapsed. and the singularity formed. However, before the singularity formed, what is called an event horizon developed, and what you have is uh, what is known today as a black hole. Uh, this outer surface that you see is the event horizon from where there is no light supposedly escaping. When you say that we see the black hole, it is really the light which is coming from the accretion disk that is circling the black hole. But from within the black hole, where the singularity is also hidden, nothing can be seen, nothing can come out. This hypothesis was taken extremely seriously, namely that always the black holes will develop whenever the massive stars die, and this became actually the basis of physics and astrophysics of black holes. So John Wheeler, Roger Penrose, Stephen Hawking, Kip Thorne, and many others contributed to the classical and quantum aspects investigations of black holes. Even thermodynamic analogies happened. So there will be a singularity at the center of the black hole. There is what is called an event horizon that you see, and out there is what is called the photon sphere. So the standard paradigm is average stars will, the upper, you see, panel, they will become red giant, planetary nebula, and white dwarf, whereas massive stars would become red giant, supernova, and black hole. And I have, you see, not talked about it, but they could all, I mean, if the star is about 8 to 10 solar masses, it could become what is called a neutron star, on which further matter could accrete, and then it could again become a black hole. But mind you, uh, this is still a hypothesis. Uh, in general relativity, there was a proof by Roger Penrose that whenever a star collapses, by I mean what are called singularity theorems, by Roger Penrose, by Stephen Hawking, and Robert Garrosh in USA, the theorems say that when massive stars collapse, what should develop is a space-time singularity. And also in early universe, such singularities will form. But mind you, nobody proved really that when massive stars develop, uh, a black hole will develop. That is an event horizon covering the singularity will happen. So the cosmic censorship remained a hypothesis uh, for decades. I think by now, almost 5 decades, and it remains one of the most unresolved issues in modern astrophysics and general theory of relativity. There is no proof, so to say, for this hypothesis. All the same, uh, the scientists were fully aware that this issue remains open, namely, do all massive stars collapse to black holes? So, you have to, when you ask this question, you have to take inhomogeneities, the internal pressures, and you see other factors, physics of star. And in past decades, much work has happened, including our own work, the work of myself and our collaborators and students and so on, as well as many international groups. And what turns out is that typically, when you consider more realistic collapse as compared to the models considered by Oppenheimer and Schneider, then in that case, in some cases, the singularities that form are covered by the event horizons, but in other cases, it is not covered by the event horizon. Uh, It all depends on the internal dynamics and the internal constitution of the star. Uh, to give you an example, if the star is completely homogeneous in its density, say right from center to the boundary, if you take the Oppenheimer-Schneider model, it was that. Then it will become black hole. However, if you have the same dust configuration, pressureless dust configuration with density somewhat higher at the center and then decreasing away from the center, which is the realistic, astrophysically realistic configuration, then a large number of models have been worked out where in fact the event horizon is delayed and the singularity becomes visible part of the time. Then it can be covered, or in some models, in fact, it could be visible for a long time. Now, all these issues have fascinating consequences in the sense that if it is black hole, how it will affect the dynamics of galaxies and their centers. If it is a singularity without a horizon, which are nowadays called also horizonless compact objects, or you see, purely singularities rather than calling them naked singularities, they would have immense astrophysical applications. I cannot go into the details of this due to the limitation in time, but partly we'll try to cover it in the question answer session or maybe even later. But here the first equation, you see, includes the inhomogeneity in the density configuration, and the last equation here tells you that in that case how the you see event horizon is affected. Let me skip this slides, but just tell you that so many models by now have been studied both analytically as well as numerically with different equations of state. You see spherical stars as well as non-spherical collapse models. They all have been studied. The key point is what turns out is that depending on what the initial data is, what the initial configuration is, depending on that, either a black hole or a singularity will develop. So you see, here is the initial surface, that is the time from where the star starts collapsing. So depending on the velocities of the shells and depending on the densities and the pressures, you see either the event horizon will form or will not form. In the, you see, space of initial data. By space of initial data, I don't want to become too technical. It is just what the densities are and what the pressures are from which the star starts developing. So, you see, these are the singularities without horizon, and you see the upper part is black hole. So you can see that each of them develop. uh, we have had you see many discussions with eminent you see physicists. In fact, in a recent interview, Roger Penrose in fact pointed out, this was the interview to New Scientist. I will not show the that part of interview here because it will take you see few minutes. But he actually pointed out that you see he was well aware of this question, and in fact he only asked a question whether a massive star will become a black hole or it will become a singularity without a horizon. I would urge you to seek out. I can send the link to the organizers who can post it to the participants. But he clearly accepted the Professor Penrose accepted the possibility that both black holes and singularities without horizons can occur. So to modify the previous picture, heavyweight stars will go either to black hole or exploding fireball. Now, why I call it exploding fireball? If the singularity is visible, so much density, so much you see temperature, so much happening will be there, that quantum gravity effects could make it explode, as I'll point out to you. It's a very emotional subject, a very hotly debated subject, when Stephen Hawking accepted that yes, such singularities can develop without horizons. It became a first page story for New York Times. I ended up, because of our work in this area for quite a while, writing, monographs for the Cambridge University Press as well as the Oxford University Press. Based on that, I ended up again writing an article. I was invited by the Scientific American, 170 years old, venerated magazine of US, and interestingly, they made it into their international cover story. This is the German cartoon as well as the title page. And interestingly, in US, a lawyer, Sergio de la Pava, wrote a novel which attracted quite some attention, and recently even a movie has been made. So this was all theoretical background. By now, it is well accepted. I think it would not be exaggerating to say that people are exploring both black holes as well as horizonless compact objects. The key point, many of you will ask, all right, these things can happen. So what? What we are going to observe out there in the skies? Are there going to be observational signatures? If the singularities are there without horizons and so on. So, what are the observational and astrophysical implications? Can we distinguish them, in fact, in the skies? So, as I said, the answer is possibly an affirmative, at least in the sense that a large number of efforts have taken place to decipher and distinguish the accretion disk properties around black holes and singularities, high energy particle collisions around singularities have been examined. Gravitational lensing around this object has been explored. Most importantly, shadows. You see, the latest excitement is the Event Horizon Telescope probing the center of galaxies. Our work with Professor Ramesh Narayan of Harvard and Daniel Malfarina has shown that singularities also can cast shadows which are similar to black holes. And in their latest series of papers showing the pictures or photos of images of our galactic center black hole, the Event Horizon Telescope series have cited our papers. The accretion disk differences are very striking. If you had a Schwarzschild black hole, as you see in the inner part dotted lines, a Schwarzschild black hole energy will stop coming because of what is called, the photon sphere and inside ISCO, innermost stable circular orbit of the matter accreting around the object, the black hole. However, in the case of a singularity that is visible, the stable circular orbits extend way below, very close to the singularity. As a result, you have much more powerful emissions in very high frequency energetic outcomes. You can see this in some of our papers. High energy collisions have been examined, and it is seen that without fine tunings, you can have a very, very high energy collisions in the vicinity of a singularity. This is as opposed to the black hole case where you have to do a lot of fine tuning actually if you were to observe uh, the high energy collisions. Gravitational lensing has been studied in great detail around earlier around black holes, but now also around the singularities. Uh, why all this is so important? So that is the point I come back to probably again. You see, this so-called cosmic censorship is absolutely fundamental to the modern theory of black holes, is its astrophysical applications. So, I mean, after all this gravitational collapse model, the study of all this gravitational collapse models, uh, if at all in some form the cosmic censorship is correct, it will, you will have to avoid these models. So you will have a very fine-tuned version of censorship. But on the other hand, you see singularities without horizons are available, visible. If they arise in nature, then there could be exciting observational implications, which are in fact already being studied. uh, Key point: general relativity implies existence of space-time singularities, strong gravity regions, where both quantum gravity and you see uh, general relativity in fact come into their own at this low energy scales on Earth and planetary system and so on. You don't observe this quantum gravity effects, but near singularities this will be really really important. Now, if this are visible to external observers in the universe, then it could have very interesting consequences. As Robert Wald pointed out, if censorship fails, then in a literal sense we would come face to face with the laws of quantum gravity, where whenever gravitational collapse to a naked singularity occurs in distant regions of our universe, we have called these objects really quantum stars. That is when singularity becomes visible. Star collapses, exciting observational implications, and high energy explosive cosmic phenomena should be observable. Does nature produce a quantum star whenever a massive star collapses? We studied quantum gravity effects near uh, such a horizonless singularity, and what we actually showed was effective pressures are so huge negative that a burst like scenario actually develops. So there is a tentative comparison, I mean, tantalizing comparison with so-called gamma ray bursts. Many such possibilities are under exploration at the moment, which you can see on the Google or on the archives. Is this a quantum gravity lab? Uh, Worth asking a question. We have not been able to make good progress with string theory or loop quantum gravity, on purely theoretical basis. But if you observe, if the nature has provided us with a quantum gravity lab, and if we do observe some, signals coming from ultra dense gravity regions, in that case, possibly we can, derive a better theory of quantum gravity with more realistic observational input. I will come to, you see, the latest part, which is, in fact, the uh, Event Horizon Telescope observations of the center of our galaxy. Uh, this is a collaboration which puts together radio telescopes across the globe and tries to explore and see and examine the very center of our own galaxy as well as M87. These are the two uh, galaxies which have been probed. Uh, they have images something like this, as you are aware. Uh, I have discussed many of these aspects in, one of my books, which is a popular, semi-popular book published by Oxford. But the point is that what we have shown is that not just the black hole, but the horizonless compact objects, that is the singularities or compact stars, also produce such images, in fact. And this has been a matter of a great discussion. In fact, in their papers, the Event Horizon Telescope did cite our papers, saying that the one of the singularity models that we proposed, that is by Joshi, Narayan, Ramesh Narayan, and Malafarina, that has been one of the best mimickers of, the galactic center object. Trajectories of stars have been studied. You see, we are talking about some of the observational implications of the singularities as well as black holes. They have been studied, and is a very interesting phenomenon pointed out by one of our, collaborators, Parth Babania, that there could be negative precision when you are dealing with a horizonless compact object. And this is again an intriguing happening. Coming to gravitational waves, many of you have seen this, observatory LIGO picture, the massive objects coming together and colliding and producing data, which is, you see, the signatures of the gravitational waves being produced. Kip Thorne, in fact, has been very, very open to the idea of, both black holes and singularities. In fact, in one of his talks, he pointed out that if you consider the trajectories around a black hole, the waveforms will have a certain variety or certain profile. However, and this is, by the way, a slide from Kip Thorne's lecture. He asked this question, that what if the central body is not a black hole? For example, if it is naked singularity. So in that case, he conjectured, and several investigations are going on as to, how and what kind of, trajectories will happen around such singularities without horizon. So he pointed out there could be a very wildly different map emerging. Now, probing the galactic center is one thing, as I showed you here. This is one thing, because the smaller the object you want to examine, the bigger must be the size of your telescope. If you want to explore the center of our own galaxy, then what happens is you must have a telescope which is so large as the size of the Earth itself. And only then you can create an image which is something like what the Event Horizon Telescope reported. However, if you want to explore actually an object like this, when I say object like this, what do I mean? when a star collapses and produces a black hole. You see, these are called stellar black holes. This object is a star-sized black holes which would have mass of say 5, 10, 20 solar masses. However, the black hole here, you see, will have millions of solar masses in the uh, in its total mass. So this is a galactic black hole. It is also called a supermassive black hole. So supermassive black holes could be there at the centers of the galaxies. But then when you want to observe a star-sized black hole, you see something like this, then it is impossible to figure this out. It is impossible to figure this out using, you see, the telescopes that we have on Earth. You can't actually get the image of such such an object, because the resolution required would be extraordinarily, you see, finer as compared to the galactic size black hole. But you will know the properties of such objects only through what are called accretion disks. That is, the disk that is, you see, the matter that is, you see, rotating around the black hole, is something like this. Here is a singularity, and there is all the matter uh, circling the singularity, and somewhere, you see, out there could be an event horizon, or maybe it is not there. Who knows? It depends on the configuration of the gravitational collapse that created this singularity. So the property of the accretion disk will allow you to decipher the nature of the object, and that is where you see a lot of work is being done. By the way, for this book, I also requested Oxford to produce an Indian edition. This has been reviewed by Nature, by Physics Today, and so on. I hope the Indian edition may be still there. But the important point that I am trying to make is that now various groups, you see, throughout the globe. For example, polarized image of equatorial emission in horizonless spacetimes. So, what are the signatures? What are the kind of polarizations? How the images are working and operating? So many such questions are being probed by many different groups using both analytical as well as numerical methods. We have many of our collaborators, students, postdoctoral fellows, who very excitingly and interesting contributions they make. I think for the moment I should stop here, and maybe if there are any further interesting points as we go ahead, then we will discuss these issues. Thank you very much for again this wonderful opportunity.
Thank you. Thank you, Professor, for your brilliant and truly inspiring lecture. And I would like to express my sincere gratitude to you for sharing such profound insights and for enriching us with your perspectives. Thank you once again.
Thank you.
So, now a gentle reminder to the audience, you may continue submitting your questions by scanning the QR code displayed on the screen. Alternatively, the Google Form link has been shared in the chat box. This question is by Mr. Louis Marmot from the York University. He's asking, thank you for this very on his presentation on the assumptions involved in the hypothesis of black hole formation. We do observe dense mass concentration in astrophysics, AGN, neutron stars, etc. But is it possible that a black hole never has time to form?
Yes, yes, that is definitely a possibility that the you see black hole may not have time to form, or the star may evaporate entirely. You see, before the collapse actually happens. Uh, But by and large, it has been accepted that when such a massive star is there, out there, and it has existed its nuclear fuel, then in that case, uh, such a catastrophic collapse occurs, and there won't be enough time for all the matter to be radiated away. Uh, Therefore, in fact, the black hole paradigm is gained so much of power. Uh, the event horizon must form, the singularity must form. This is the crux of singularity theorems of the Penrose, Hawking, Garrosh. That you see, if the trapped surfaces form, then the singularities must develop, unless there is a very violent disruption of energy conditions. If the quantum gravity gives rise to very strong negative energies, then only the singularity can be, or the black hole can be halted. And that is why you see the so many astrophysical applications of black holes came into being. Catastrophic gravitational collapse is the key thing.
Okay, okay. Thank you, sir. So let's move to the next question by Dr. Bharat Pandey from Government PG College Raniket, Uttarakhand. So he's asking if black holes are the final stage in the life cycle of massive stars, do they truly represent an end, or could they actually be a transition phase where matter and information are transformed into something where we do not yet understand? In that context, how does this idea connect with current theories about information laws and the possible existence of new physics beyond our observable universe?
Definitely, the physics very close to the singularity, which might be hidden within the black hole, is unknown as of now. Uh, Whether a black hole would transit into something even more mysterious is an open question. Uh, there have been issues and there have been conjectures even regarding the you see transition to another phase, uh, but theory which really works out the you see the consequences, it is yet to be formed. There are issues, I mean there are questions, wormholes, and you see the loops, the topological tubes, and many other possibilities have been discussed. But yes, it's still an open question.
Okay, thank you. Thank you, sir. So now let's move to the next question. This is Mr. Ajay from Department of Physics, SVNIT Surat. So he's asking, why is that when something entering a black hole stretches in its front and back like a rubber band, if it is due to its strong gravitational pull, why is it not in the case of massive stars?
Yes, near the black holes, you see the gravity grows enormously. So typically, you see this so-called gravitational tidal effect is always there. That is, if you have a rod hanging in a gravitational field, and the one end pointing to the center of the object, then the gravity at the closer end would be higher than you see the gravity at the other end. But this is a very minute difference in gravity. When you are really near a black hole, then this difference or the gravitational tidal difference grows so enormously that it really stretches away the object. So it is the difference really in the gravitational pull at the both ends of the object. And this is why you may have seen the pictures that the man falling in the black hole is completely stretched, you see, and becoming like a line.
Okay, thank you. Thank you, Professor. So now let's move to the next question. This is by Miss Sweta from Starscape Experience. Thanks for such an amazing lecture. My question is, you have long argued that under certain conditions of stellar collapse, a naked singularity can form instead of black hole. If the Event Horizon Telescope (EHT) continues to provide images that look like shadows, how can we observationally distinguish between the shadow of the traditional Schwarzschild black hole and the naked singularity that might be mimicking that same visual signature?
Yes, so this is in fact a very interesting frontier. How do we distinguish shadow that has been created by a singularity as opposed to that created by a black hole, even though they may look similar in sizes, in the in their appearance and so on. What some groups have been probing, as I am mentioning, as I mentioned during the talk, right now many groups you see around the globe have been exploring uh, these possibilities of distinguishing these two objects from each other. Now, uh, the point is that these gravitational fields are described by, you see, what are called the geometry of space-time. Like the Schwarzschild black hole is described by what is called Schwarzschild geometry. There is a particular metric. It is called, gravitational potentials are there in the geometry which describe what kind of gravity is there as you move from point to point. So the gravitational potentials of the Schwarzschild geometry are quite different from the gravitational potentials of a singularity spacetime, that is a horizon-less compact object. And you see, one difference that I pointed out to you earlier in the talk, if you remember, is that the accretion disk extends way below, inside, very close to the singularity. The stable circular orbits extend way inside. So that is why the output of the accretion disk is quite different in the black hole case and the singularity case. However, further, uh, when we have, for example, you see, the other finer images, you see, of the central object which is at the center of the galaxy, then if it is, you see, a singularity, naked singularity or a horizonless compact object, then there will be some very definite differences arising as compared to the Schwarzschild geometry. We are, in fact, some groups are already exploring these differences. And this work or this, earlier, you see, I should tell you a little bit of, history in the sense that even though I might have, you see, pointed out to you some results, uh, it has been, a very uh, standard assumption in the field that, well, if the massive star has collapsed, then it must be a black hole. But of course, everyone agrees that it's a conjecture and it's a, hypothesis. Now, all that we have done is we have explored, and also many other groups. So it's not just me that I have argued. It is the group of scientists at various places by now. numerical, you see, efforts even from Oxford, Cambridge, even at Princeton, you see, Institute of Advanced Studies, detailed numerical simulations have been carried out of collapsing objects. In fact, in string theory today, it is widely accepted, the results have been there, that in the dimensions higher than 4, naked singularities are extremely common. In string theories, that is the result today. So by now, the subject is much bigger, in fact. Uh, so I am just an insignificant, part rather than my arguing. So it is the, I mean, it is true though that I have worked on these issues for many years. So uh, the key point that I was trying to make was the finer differences in the images of a black hole and horizonless compact object. This will come out when we do further analysis. And because Event Horizon Telescope has cited our papers now as the best mimicker, so the attention has been drawn. And now these investigations have begun. Yes, but it's a frontier question. Thank you.
Thank you. Thank you so much, sir. So now let's take one last question. This is by Mr. Kumar Ravi, and he's asking that suppose we postulate that no physical system in the universe, including the universe itself, can reach a density greater than that of an atomic nucleus, thereby eliminating singularities in black holes and the Big Bang. Would such a hypothesis still be compatible with the key black hole observables such as gravitational waves detected by LIGO, shadow imaging by the Event Horizon Telescope, and the orbital motion of stars around Sagittarius A, or can it already be ruled out?
Interesting, a very interesting question. In fact, the possibility number 3 that you have mentioned, the orbital motion of stars around Sagittarius star, it kind of fairly definitively point to the existence of extremely high dense plasma or the matter close to the galactic center. Uh, and again, you see, if you see this particular book, you see that I showed this Oxford University Press, or the book by Kip Thorne on black hole, time warp, and you see other issues. If you see this, Kip Thorne argues very, very strongly as to why a catastrophic gravitational collapse must give rise to ultra dense regions in the universe. However, people have tried throughout to avoid and resolve space-time singularities. My final say, uh, well, not final say, but it is subject to the, I mean, I would say the strongest possibility would be that when the densities grow sufficiently high in the gravitational collapse, then the quantum gravity effects will take over to really resolve the space-time singularities. But still, this will be extraordinarily high densities, way, way beyond the, you see, the usual atomic scale densities. Thank
Okay.
you.
Thank you. Thank you, Professor, for addressing these questions with such depth and clarity. On behalf of Bhaktivedanta Institute and all the participants, I would like to once again express our sincere gratitude to you for sharing your insights and wisdom with us today. Your lecture has given us deep insights into our science and understanding of the universe, and we are truly grateful to your time and generosity. Thank you very much, Professor Joshi.
Thank you. Thank you so much. I thank all of you and the Institute. Thank you.